And it is so awesome having Phil Mulvey joining us today. So with over 35 years of leading teams of dedicated scientists, technicians, and managers working on problems in environmental geoscience, Phil's goal is to inspire people both externally and internally within the companies that he has co-founded, including Environmental Earth Sciences International, Carbon Count, and 3D Ag, to find innovative ways directly or indirectly to rehabilitate 10% of the world's degraded land by 2034. So it is going to be totally awesome hearing from him today about the Mary Kathleen Uranium Mine Closure, 40 years on, by the geochemist who designed it. So this is going to be a great session. I hope you all enjoy it and take away some great insights. Keep using the chat. We'll open up the floor at the end. And yes, thank you so much, Phil, for joining. It's amazing having you.
Thank you, Jessica. It is indeed a pleasure to be invited. And it's actually been a pleasure to look back 40 years. So I'll switch. Am I on screen at the moment? Is share at the moment?
No, the share's off now, so we'll have to re-fire that one up again.
Okay. Hopefully that's
brilliant. Yeah.
Well,
perfect.
Like Jessica, I would like to pay my respect to elders past and present who believe in nurture and rehabilitation of landscape from whatever basis they come from. This is a recent shot of Mary Kathleen. It's hard to imagine, for me anyway, that this was the start of my career. And literally across Australia, almost no rehab had been, or intentionally closure had been considered at the point of time that I started. There's a further shot from the pit. As you can see, visitors come along, are told it's radioactive, there's falling rocks, given it's a 55-degree slope pit. Yes, it's pretty sharp. And so it was designed not to actually go and have a swim. We'll talk a bit further about the minerals because I'm a geochemist, environmental geochemist, so I love looking at a bit of minerals, and so there's a lot going on. If you look at the bottom left, you can see a bit of copper carbonate there, but there's a lot going on in the shot, so we'll start to talk a bit about it. What we didn't predict was weeds. Weeds were not considered at all very early on, so I'll talk about also some of the issues of weeds. But let's look at Mary K, because it's quite unusual. It was MKU or Mary K. We used to wear shirts and the contractors as well, which was U308, which is called yellow cake. So U308, we bake a good cake, was what they used to wear when they played Mount Isa and Cloncurry and the various sport events. It started in 48. The ore body was found in 54. The government actually had a share of it because you couldn't own uranium otherwise. It went into care and maintenance in October 63, and that's very important because the word environment didn't actually exist in the 50s, and you didn't actually make a mine on the basis that you actually had emplacement facilities, you actually had dumps. It recommenced late 1974. Closure planning sort of started in 79, but got more underway in 81 when I was part of the team that went to site. Closure planning started from that period. It was completed in late 84. That's a mistake there. With the lease relinquished in April 87, monitoring was supposed to be continued by the department, which only just started happening in the last year or two. It was owned by CRA, which became Rio Tinto, and the Australian government and the public. It was a primary uranium ore. It was uranite. And that's unusual in Australia. There's not many primary ores in the world. They tend to be roll front-based ores, as in the Northern Territory. So for that aspect, it's quite rich in rare earths, as is the tailings dams currently. So there's various times people come back to look at it for rare earth mining. Up until that point in time, no hard rock mine had been closed. Some coal mines and Alcoa and some East Coast sand mines, but nothing had been properly closed. And acid rock drainage was nascent. I did my thesis in 79 on urandry, on environmental investigation of it with the acid mine drainage, and I think that was the first thesis in Australia at that time on it. The sulphide contents were 0.5 to 1.3%, and the acid neutralisation capacity was 3.5%. The mill operated a sulfuric acid and manganese oxide extraction, which is very unusual, that you actually have conc H2SO4 and a very, very strong oxidant of manganese oxide. So you had two oxidants together. They had pit, waste dumps, borrow sites for the waste dumps, plant, operating mill and facilities, crushing plant, tailings, number of evaporation ponds, towns, associated roads, etc. The town actually shouldn't have been closed, but it did. People wanted to keep it. And back then you had mine towns. They didn't do fly in, fly out. You went and stayed at the mine. And that was the way it was. What was the state of play for mine closure in the early 80s? Well, the first conference in the world on mine closure was 76. The first journal to write about mine closure was this one in 79 during the writing of a thesis. And as you can see, the first look really at metalliferous mines and acid area mine drainage was from Mount Whaleback and the Woodlawn mine, which remains a problem to this day. Most of the rest was about open pits or gemstones, which are pretty easy. So it was interesting looking back what was the state of play. Let's jump to Mary K itself in principle. So you can see that there is the town, a little distance away, the mine, there was the big freshwater dam a bit further away. You've got the mill area, a number of waste rock dumps close at hand. You've got the tailings repository, evaporation pond number 1, evaporation pond number 2, and then you've got this Cameron Creek River going through with a couple of rock bars, and they're actually important. It sits in a fairly calcareous and limey material in a base of granite. So it's a liming intrusion into a granite, and it's Paleoproterozoic. So zooming in a bit on the features, a bit more, you've actually got the tailings dam, the evaporation ponds, you've got the mine, which as I said is quite steep, and you've got the waste rock dumps surrounded round. Back in the 50s, fairly simple. If you had a creek gully, you just put a dam across and you filled it. You didn't line it, you didn't worry about investigations, you didn't do anything. You just filled it. And that's pretty much what happened. And so you've got this dam and this evaporation pond sitting straight across this riverbed. The riverbed is in a calcareous red earth. Thank our lucky stars it was. So it was full of calcrete pebbles, and the clay was quite a rich illite kaolinite, so it had good absorption capacity, a little bit of smectite, and it had a hell of a lot of calcrete in it. In principle, the kind of model we're working with, you're doing with the pit, the waste rock dumps, the mill, they sit on shallow soil. The evaporation ponds and tailing ponds also sit on alluvium. You've got a rock bar where it all comes out again. It goes under the alluvium before a second rock bar, it comes out again. So that was sort of the basic model that we're working with. Hazard features that you would look at these days, which we started in those days as well. So we looked at the base of the pit to see if we could, what the permeability was. So as the final stages of 82, we're down here at the base, drilling out on the angle, trying to connect across to another fractured zone to see if we can ensure the pit was constantly dewatered. That wasn't the case. You can see how steep the wall is down the lower level of the pit. Evaporation ponds had monitoring going on from the 50s. It was just a 44-gallon drum that you filled with cement. It's a little bit more sophisticated these days. And you can see that even in the 80s, we're doing with a fair bit of salt build-up from the sulfate from the adjoining evaporation pond. So we've already got breakthrough. So we're dealing with acid water. That drum had been there for 2 weeks. That's what remains. So it was quite low pH water that we're dealing with. You can see OH&S was pretty dear to our heart back in the 80s. And this is working on top of the tailings dam, doing a technique known as sludge pumping. And you can see the salt, you can see the black rock surrounding it. Got to 50 degrees there some days in November and December. We're working across that. Being thixotropic, you can't get vehicles out, and you can only do techniques by hand, and we have to stand on pallets as we're going up and down because the pallets would sink. So the key issue not fully understood when you look back, and this is to deal with even current people looking back to slavery, to how we treat the Aboriginals, how we arrived in 1788, is we tend to judge on today's standards. So the philosophy of closure was very different in the early 80s. A key problem is Mary K was never designed for closure. Waste was dumped, it wasn't placed. And as I said, environment was a name that wasn't even thought of. So environmental and earth sciences, our business name, when I registered it in 84, there wasn't a single environment in that thing called a phone book, which doesn't exist anymore. So it was easy to take whatever name you wanted with environment in front of it, because even New South Wales EPA was called State Pollution Control Commission. So the name environment, its concept, did not exist. So that meant the philosophy we proposed was not encapsulation with zero release, which is what's considered now, but controlled seepage and attenuation zones. So it was a different philosophy approach. And we didn't intend for the waste rock dumps to fit in, because we wanted to look like a mine site, because we couldn't have people camping on the tailings dams with high radiation. So the concept of having it fit in was something that actually we didn't want at all. We wanted to stick out for at least 100,000 years because it's a radioactive facility. So the philosophy approach was quite different to most mining today. So this is an emplacement facility of a few years ago. It's a 10-year-old shot, but you're dealing with non-acid forming waste on the bottom. You're dealing with a clay liner. You're dealing with acid forming waste going over the top. You're dealing with encapsulation as you go. So all that's carefully designed. We did not have that opportunity at Mary K. It was dig and dump. And it was from the 50s, and we had to address that as it went. So we zoom in on this model again on what we're looking at. And this is what we set out to investigate. We did a whole series of investigations in the 80s. But we've got to look at what we started with, because this is pretty noxious stuff going out. So because the treatment's conch, sulfuric acid and manganese oxide, and pumped at 30% solids, because we didn't have sophisticated dewatering techniques then, it was also quite hot. Temperature was 80 degrees C when it went out. pH was less than 2, in some instances less than 1, depending on what was happening. The PE was greater than 7. So PE is fancy geochem terms for platinum electrode redox. So that means it was greater than positive 420 millivolts. The TDS was 100,000 to 120,000 milligrams per litre. Iron, manganese, and aluminium were between 5 and 8,000. And I was stupid enough, I didn't measure silica. But silica would have to have been over 5 to 600. So it was a sodium sulfate dominated water, exceptionally corrosive. It got through a pair of socks in 3 days, and we had a new pair of boots every 3 weeks as it wore through what we were working on. The guy on the right with the beard, he's still alive. He's 85. The guy on the left, who was a smoker, I don't know if he's still alive or not. I haven't been in contact, but hand digging down to 16 metres in tailings, it's hot, both radioactively and water-wise, is an interesting exercise in itself. It would not be allowed today. Here's a series of piezometers that we've put across the tailings dam. As you can see, there's, I think, 16 on a traverse going all the way across the liquid tailings. Interesting enough, the sulfides start sort of around 1.5% and drop down and oxidise as you go down. I'm surprised they were so high to start with. The 1963 crust line where the jarositic layer formed is very interesting, and what's happening below it. From a multiple interesting point, and there's a little bit of chalcopyrite in the system. So you can see the sulfate also starts high but washes out. and the water table is quite close to the surface. So this is a set of tailings off to the side. This is a modern from a quite large, one of Australia's largest sulphide mines. And the interesting thing about this tailings investigation, so this was at deposition, whereas this is after deposition, measured down the tailings. So we've actually drilled down 17 metres, collected samples and sent them off. This is measured at deposition because no one's got on to measure this particular tailings dam. It was still active a little while ago. But in this occasion, you're going to the transitional zone, which actually, I assume everyone's a miner here, so I won't explain all this, but transitional zone is the area which the water table moves up and down with time. And some of your sulphides are gone, and you're dealing potentially with carbonate and oxide minerals and a little bit of pyrite. So you can see that this tailings dam doesn't make acid. Then they got more efficient in extracting the pyrite, the iron out, because they want to concentrate on the zinc and lead and copper. So you end up with a circumstance where you get this variability. And finally, they moved to the primary zone, and they didn't actually tell anyone, and they didn't tell the environmental department that they'd changed the whole process, and you end up with the top of the tailings gone acid. So that's what you see on a more modern tailings dam with depth approach. This was the historic one where we measured in situ, not what was being placed. So when you look at what pH does with time, there's a series of different holes we've looked at. Some are wet and some are dry. The wet ones start with quite a low pH, even though it's limey with a huge excess of carbonate. And the dry ones have already been buffered a little bit. You see with time, you're seeing all this buffering capacity occurring. This is data from the time, so we knew that the system was self-buffering. We knew it rose quite quickly to 5.5, 6, and there's reasons for that, the precipitation of goethite. So you're seeing that the system is being neutralised by a variety of mechanisms. The redox under the wet is highly oxidative, and under the dry is less so. So once again, you're seeing the redox of depth. And the interesting thing is that once it gets past this level, it gets to the point where you're heading towards reducing conditions. So something odd is going on with Mary K tailings. In themselves, this data set's not being published. It's actually the 1981 data set. So it itself is quite interesting in seeing the impact of hard layers and the fact you get H2S venting from below that hard layer. So the tailings dam model was itself quite complicated. And the beauty about this whole system, it was done right at the point that Apple II computer came out. And we could then run models at the desktop, which we couldn't do before. We had to use punch card mainframes. So that opened up the whole modelling for environmental works to look at what was happening. The model was quite complicated because you hit a series of upgradient lifts in the tailings dam with intermediate earth dams placed directly on tailings. You also had the old layer in here, and you had flow going along the base. So you had a series of interesting scenarios going on that had to be modelled on the very early days of modelling. So all this was done in Fortran without sort of going through ModFlow and those things which didn't exist then. So the interesting thing about it was, yes, we did a lot of holes investigating. We also put riprap over the top, not to seal it, because we had to keep it moist to keep the radon gas in place. So there's a lot of issues associated with why we left it the way we left it to ensure that radon gas didn't emit. Because what happened in the tailings, as you'll hear in a sec, is that it sorbs the radium, and the thorium and polonium go to the evaporation pond. So the main radioactivity is associated with the tailings. The really interesting thing about it was that the Mary K ore does not contain aluminosilicate. It's a primary rock. And so it doesn't contain them at all. It's just straight silicates. But the tailing discharge did contain secondary aluminosilicates. It contained both smectite and kaolinite. And at that stage, there was a textbook just released in 7980, which was on thermodynamics. of clay minerals. And no one had actually predicted you can form clay minerals very, very quickly. So neogenesis of clay minerals is something that sits in the Mary K data that took me 30 years to analyse. The radium was concentrated in a less than 10 micron fraction, which we knew. So these were these rapid form pseudo-clay minerals. If you look at the stability of aluminosilicate secondary minerals, and you look at the pH range associated, and you look at what's the raffinate, which is the water associated with the mill, you would see in the raffinate you are precipitating both kaolinite and smectite reasonably quickly. And then the tailings dams, you start to precipitate a little bit of smectite, but mostly kaolinite as the pH comes up. So very, very interesting what was happening in those tailings. So that meant that acid tailings for uranium mining scrubs radium. So Mary K did not have the problem of Elliott Lake and Ranger in the early days with neutralized tailings where the radium follows gypsum precipitation. Here it actually directly followed the particulates and stayed and was non-leachable. Really, really fascinating stuff. It took 15 years to convince Ranger to change over. The aspect of neutralisation not really known for ARD, and this is from a paper I gave in 2009 at the International ARD Conference, is, and this is based on acid sulfate soil, but as you go into the neutralisation pathway coming up in the soils of especially acid sulfate soil or mine waste with time, you actually get to the point that neutralisation starts to be controlled by this precipitation of kaolinite and smectite, which brings it up into that pH 6 range. So even though there's no carbonate in the system, if you've got a semi-closed system where the silica stays in place and not gets washed away, you end up with kaolinite and smectite being precipitated. So in principle, we're going to cover the tailings dam, neutralise the water with a few techniques I'll talk about, and then cover it and walk away. That was the general principle. So the evaporation ponds sit across here, as discussed, with all its monitoring around them back in the 80s. We knew that we had all this calcareous red earth all around the region with this heavy clay in it. So I had a brilliant but stupid idea. Often ideas are like that. You think they're brilliant initially, then you realise later they're stupid. Anyway, so the bottom line is we put in a lot of long trenches along here to infiltrate the water through the calcareous red earth and the calcrete to neutralise the acidity, then collect it all up once it was neutralised and put it back in the tailings dam. So we did a long trial in 81. We injected it in the ground. It behaved beautifully. We had a Clostridium species algae appear here, so I was going around collecting all these algae and sending them off to universities because no one had ever seen this stuff before. There was an algae bacteria association that actually precipitated manganese, which was later used in a manganese dioxide plant. That was a little side note. Anyway, we had a whole series of piezometers watching the infiltration rate occurring. And you can see we put these up around the hills to infiltrate. Well, I was a bit stupid. I forgot about it. This is my first major mistake in my career. It only cost a couple of million. But anyway, I forgot about gypsum. Gypsum lined the bottom. It stopped infiltration occurring at the same rate and encapsulated the calcrete, so it no longer reacted. I'd actually forgotten about simple chemistry, but anyway. So they decided, well, how do we get rid of the rest? So we decided to increase the surface area of the ponds. pH now is around about 2. pH, both ion valencies are in solution, and so the water turns red. So you've got this reddy orange colour. It's producing vast amounts of jarosite on the bottom, so we pushed it out to evaporate it. We didn't allow in our modelling to what would happen to the sludge. So all the sludge on the bottom was picked up and was put in, as you can see this red water here, was put into the upper part of the tailings dam, which actually played havoc with our modelling projections. So we put it up in here. we hadn't actually considered what that would do to the whole system. So that was the planning. A lot went into it. A fair bit of money was spent. The first investigation that I was geochemist for was $300,000 in 1981. And the closure campaign itself was $16 million in 1981. Now, it doesn't sound much money today, but when a media beer was 19 cents and my gross income was $14,000 per annum, that's a fair bit of money. So it was a huge amount of money to be in charge of as a young graduate, having no idea what I was doing. And luckily I had some senior people who weren't geochemists, but who steered us in the right direction. And closure went ahead, and a lot of money was spent on the procedure and how to go about doing it. So jump forward to 2006. Unfortunately, these are reversed. It should be the other way around. I didn't get time to change it. Here's the tailings dam, the evaporation ponds. There's evaporation pond 1. There's a bubble up at 2. You can see some salt scarring up here, which I don't think is associated with it. I don't actually have a water sample from up here. You can see the impacts of the bar 1 and bar 2 down there. 2012, drier period, a bit more exposure, particularly around the mine mill area. The zoom in 2006, the tailings, you can see there's some weeds, which we'll talk about in a sec. You can see the seepage point from evaporation pond 2 and seepage point from tailings dams. Lake, there's no pit lake back in 1981, obviously. There's now a pit lake. So let's look at 30 and 40 years on. Some researchers visited in 2012 and said the whole thing had failed. I kind of find that a bit upsetting. So over the period of years, various members of our staff, when we were close at hand working on the mining work, went and collected more data. So let's have a quick look at that and what they said. So a sampling point, obviously the pit here, the interface of the two, depending on the season, and Cameron Creek upper and lower, but we didn't actually get all the way up to here to get a Cameron Creek sample. It was a bit hard, and there's a lot of salt in the district and also a lot of sulfides in the district. So TDO1 is the tailings discharge. TDO1, it's sort of in the general area, is a seep from evaporation pond number 1 to evaporation pond 2. CDO4 is Cameron Creek upper, and CDO5 is between the two rock bars. You can see the rock bars signed there. And pit, well, that's the pit sort of thing. So moving down, this is a pit shot of last year, of literally only 9 months ago. This is a fascinating slide for those of you that are totally into geochemistry, so I'll stop and talk about this because I'm totally into geochemistry. On the left, you've got the copper carbonate. If you look, and it's a greeny colour, if you look 45-degree angles from top left to bottom right is calcium carbonate veins. Where they occur, you have goethite. Where they don't occur, moving to the far right of the shot, or they start to fade out, you've actually got jarosite. And up the top, you've got a lot of gypsum. So you've got gypsum at the top being neutralised, and then you've got the goethite overprinting it at the bottom. And the right, you've got jarosite, which is your yellow colour. There's no neutralisation occurring there because the pH is 3.8. So there's not enough carbonate in the wall at that point. So when we had to model this, we were lucky enough to have a closure between 58 and 63. 63 and 74. So when they opened in 74, some smart person took a water sample. And that gave us a modelling point for the rainfall between and to work out the level of the pit. So we put in a oxidation factor for sulfides and a correction factor for carbonate, but based grossly on the pit. This was the first pit model ever done in Australia, and had geochemistry on a spreadsheet that tied into it. So it was quite interesting getting the whole thing to work. So seeing live geochemistry like this, where you're seeing the whole interplay of iron minerals scattered across the page, from goethite, and you're seeing a little bit of ferrihydrite here, and then over here you're seeing the jarosite. So this means the pH is 3.8. This means the pH is over about 4.5 here, moving to the goethite, sitting somewhere between 4.5 and 5.5, and then up to it's all this white inflorescence as you gypsum. It's actually, and then you can see all this calcite veins going through. So it's actually, I get excited about geochemistry. It's a lovely example of geochemistry in action. What we know about then was visual amenity and weeds. So let's just have a look now to our waste rock dumps, which are up to the top of the photo, up to this image on the right, and beneath the pit, so south of the pit. So this is how it looks now. You can see they're not well vegetated. You can see the pit in the background. There's a bit of vegetation on these. They're very steep, and they do stick out like dog's balls. You can see them on the landscape. So they're highly obvious, and so they should be. They're low radioactive, and it's important that people don't go camping on them. So they do have to be delineated reasonably clearly. It's not hazardous unless you're spending, years on top of them, but you don't want people in the future to come and think this is nice flat ground, let's build a house. If you zoom in close, you can see that we didn't probably think through some of the sediment and erosion issues from having steeper slopes, and that was not greatly known then. Here's looking down on the evaporation pond number 2, and you can see the coverage across it with some of the woody weeds, which we'll talk about. So here's the woody weeds we had no idea was an issue back then. So you've got the thorny acacia, and you've got Sodom's apple behind, and the only thing that actually eats Sodom's apple, surprising enough, is camels. So we attract camels to the area, and camels will tolerate more salt. And because there are saltwater springs on this particular site during the extreme dry periods, it does attract camels. So let's look at now water quality. I'm going to show you some images that aren't particularly impressive, but that's the way it is. This is last year. So this is the seep at the back of the tailings. Here's the former extraction well that pumped water up from the base of the alluvium under the tailings dam back up to the mill for processing, because they knew it was leaking at the time. This is pretty bubbly, pretty gaseous. The pH is actually reasonable, but you've got all the neutralization reactions occurring. So this is now sampled at EDO1. So that was sample EDO1. This is EDO1, as you can see it there above the F of former. This is also bubbling up along the line of the old alluvium. It's not, neither of these are acid. They have a little bit of nitrate from the blasting, but mostly that's due to stock coming in and disturbing it. But the TDS, as you'll see, is quite high in that, so it's quite high salt. That's looking all the way to the back of the evaporation pond wall. So this is within the fill of the evaporation ponds and the capping of it. And that then runs off the evaporation pond into Cameron Creek. So you can see the amount of salt that's there. You can see that we get some sulfate salt springs emerge. That's a sodium sulfate little uplift that occurs. So it running through a wick of a particular rock that's set up the right way to do that. So now we go to CD05, Cameron Creek downstream, and Cameron Creek upstream. So Cameron Creek downstream, you can see the salt coming out through the alluvium, and as a result of sitting there and evaporating off during the summer, during the winter, the dry spell. This is downstream. Once again, you've got cattle. It's a new bore put in by the government last year on the other side of the tailings dam. But we know we do get breakouts further up from the evaporation pond and tailings stand. So let's have a look at some of the data. Water quality monitoring event. You can see the pH on the pits, beautiful, and 3,500 is the TDS. TDO1, the discharge from the tailings is, you'll see in a sec, pH 7, so no acidity. 26,000, so it's certainly getting up. The evaporation pond discharge point is 8.5 because of basically the very high TDS and the high amount of sulfate, and upstream's 12,000, downstream's 8,000, but don't believe that upstream sample. We just haven't got enough to get up past it. But the whole area does contain a lot of sulfate. If you look in terms of the dollar plot relationships, you'll see that the pit is somewhat different in that it's a calcium sulfate-dominated water, and because of what's coming off the wall, whereas the rest tends to be more sodium-based or sodium-magnesium-based sulfate. So the calcium is precipitating out higher in the other systems as gypsum. So there's nothing particularly unusual about that. You have a little bit of nitrate occurring in the pit from blasting. As you can see, it comes up a bit. And there's a little bit of ammonium in these systems at the discharge point as a result of reducing conditions and manures. So you're seeing, the standard sort of stuff you would see associated with inland waters and blasting and salt accumulation. Basically, if you look at those particular points, so the pit in terms of heavy metals, pretty good, as you expect with that pH. The pit in terms, a little bit of copper, which you'd also expect, you see from the pit wall. Uranium's up a bit, which you'll expect. If you look below, that's one set of analysis in 2016, and this is another set of analysis in 2022. So you've got uranium in that water that we saw just last year is 15 milligrams per litre, which is actually higher than our prediction. I'll talk in a sec. And it's 2.9 and 1.7 in Cameron Creek, which is sort of what we were expecting. In terms of radioactivity, some interesting data. Very interesting data when you look at the behaviour in the pit, where you can see that you actually have radium leaching, but you don't leach anywhere else because it doesn't get out of the tailings dam. So you'd see it in water, but not in water associated with the others. Even though the radioactivity is much higher, it's much higher because of the thorium and particularly the uranium itself. Thorium, as pHs, tends not it's only going to be in the salts, not dissolved in the water. So interesting that it's the uranium controlling it, particularly the U-238, which is not quite as radioactive as the U-235. But we are seeing these levels in the evaporation waters. We're not seeing them travel too much, and they do drop down reasonably quickly, which is what we hope to see. But surprising enough, the upstream seems higher than the downstream. And we think that's the influence of the salts from groundwater seepage. If you look at the radionuclides, that's the scatter of how they look. The pit relationship doesn't pick up any of the U-235 component because and we're not showing the radium associated with that, so it's all associated with the tailings dams and evaporation ponds. So how does the prediction go against the measure? Well, the pit model was within water level fluctuations, which was good, within the TDS, within the pH, within the metals, within the radioactivity. And given it was the first pit lake model ever done, I'm pretty happy with that. We did use some fudge factors, but the fudge factors seemed to work. The tailings dam, the radioactivity surface, so emissions by radon were within prediction. The pH was expected, and the TDS and radioactivity, the seepage was expected. But some work was done by some researchers from universities in Queensland into the top of the tailings, and they found the sludge, and it had very low pH and was quite radioactive. So that material should be neutralised as it passes through, but we're not seeing any of the seepage. The evaporation ponds, the pH was expected, the TDS was much higher, and we're not quite too sure why it's running high. It must be the sludge that's put up, because that sludge would run 600,000 or 700,000 TDS. The mean concentration of metals and radioactivity is the same or up to double in a couple of instances. And the water predicted would be not suitable for stock, and that's turned out to be the case. The Cameron Creek, the top bars, we didn't get lower down. It was predicted to be in the range of 12,000, and we found 7 to 10,000, and we found 8 to 12,000. But some analysis in a very dry season in 99 saw it from 17,000 to 37,000. We always knew that it wouldn't be drinkable for those top 2 bars, so a new water bore was put in that vicinity for stock. So the attenuation zone was to be the second bar. After that, the water quality was supposed to be at level. Where do we fail? We failed because we didn't predict the sludge influence on the tailings, and we're not quite too sure how it's going to go in the future. We didn't fully understand the steepness of the slope and sediment issues coming off from the dumps, which was found to have a small halo of heavy metals around. Weeds we had no idea about, none. Standards have changed. So the standards in drinking water and exposure for radium and uranium have dropped to 1/10 of what they were in 1983. And the philosophy has changed as well. Current philosophy is zero discharge, which I don't believe is actually 100% achievable. And I'm much more comfortable with looking at understanding nature's attenuation of and utilising nature's mechanisms for attenuation, which was very much in the early days back in 1984 or 81 to 84. These days, we have a lot of people in go. This is just a mine audit team for a very large mine. I won't say which one. And so we have this many people involved in mine audit. We have a hell of a lot more people involved in mine closure. And so the approach, rightly so, is very, very different. And so that's a quick journey. I haven't quite got all the data fully analysed yet and put together in for a paper. We started the paper in 2013. It actually got rejected for lack of modern data, so we collected modern data. So thank you very much, Jessica and GeoHug, for allowing me to have a trip down memory lane and to just look at a set of data from 40 years ago to today and just the approach of 40 years ago. Thank you for the audience. And if there's time for questions, happy to take them. I'm sorry I blurbed on for about 10 extra minutes.
You were brilliant.
And you're welcome to send me an email.
Thank you so much. Yeah, that was brilliant and so fascinating to see, what's changed and the whole journey. So thank you so much for sharing all of that.